Section 8, the Friedmann equation. We want to know the universal expansion scale factor, A of t, at all times. Finding A of t requires solving two differential equations, partly analytically and partly numerically. This is Alexander Friedmann's 1922 first equation for finding A dot, the time rate of change of the scale factor, if we know all these other factors in this equation. Don't worry, we will not be doing the calculus. We will see how things fit together and then see the graphs for the scale factor. If you hate equations, I encourage you to at least see how the expansion of the universe shifts from one epoch to another as the cosmologists see it. And soon we will get to the graphs. This nonlinear first-order differential equation relates the scale factor, A of t, and its time derivative, A dot of t, on the left side with other time-varying values of the composition of the universe on the right side. The scale factor A of t has been increasing from 0 at the Big Bang to 1 presently, and will be larger than 1 in the future. The universe is expanding, so A dot is positive. For the last 10 billion years, A dot has been nearly constant, with the scale factor increasing between 6 and 7% every billion years. The scale factor has been nearly linear and has doubled in the last 7.9 billion years. So the value of both left and right sides have reduced by a factor of 4 in that time. The universe has been expanding because it was expanding after the Big Bang, and the conditions of the universe have not halted the expansion. We will see that. The expansion is somewhat analogous to an inertia of the expansion of space since the Big Bang, but is not Newtonian momentum of matter moving relative to space. We will see that expansion decelerated during the early billions of years. This was due to all the matter and radiation in the universe. This is analogous to gravitational attraction, but of all of the matter and radiation in the entire universe with all of the other matter and radiation in the entire universe, not just one galaxy with its neighbors. We cannot use Newtonian mechanics. We must use general relativity. In the Friedmann equation, the ratio on the left-hand side is squared, so it's positive or 0. If you're surprised to see the squaring on the left-hand side, the term within parentheses is somewhat like the expansion velocity of the universe, and velocity gets squared in the Newtonian formula for kinetic energy, 1/2 mv squared. The left-hand side is somewhat like the kinetic energy of the expansion of the universe, and the right-hand side is somewhat like the total energy minus the gravitational potential energy of the universe, but this is only a rough interpretation. The first term on the right-hand side, in blue, is the total energy density of matter and radiation, for example, light, in the universe, which is always positive. The energy density of matter includes rest mass energy, using E equals mc squared, so any kinetic energy of atoms is inconsequential here. As the universe expands, the energy density of matter and radiation decrease with expansion, as we will see. This first term, the energy density of matter and radiation, dominated the expansion of the universe for the first 10 billion years by being larger than the second term. But it no longer is. Presently, the ordinary matter density of the universe is less than 10 to the minus 30 of the density of water. The second term on the right-hand side, in green, is Einstein's cosmological constant, capital lambda. Presently, it is twice as large as the first term. We can think of this term as either a constant energy density of the universe or a constant acceleration of expansion. There is interesting history, which we will not cover, about whether this constant should be zero or non-zero, but cosmologists now believe strongly that the cosmological constant has a positive value that may have been constant since the Big Bang. Dark energy is the modern name for this term, to distinguish it from the energy of radiation or matter. You can think of it as the energy of the vacuum of space, though that interpretation has serious issues that we won't cover. About 3.6 billion years ago, the matter energy density fell below the dark energy density, and since then, the dark energy density has dominated the expansion of the universe. You might have read that dark energy is a repulsive force, repelling galaxies away from one another. That is not the way to think about dark energy. More on that later. The third term on the right-hand side, in red, is the space-time curvature term, which could potentially be negative, positive, or zero. In the course on gravitation and black holes, we saw that space-time curves in the vicinity of masses. The universe as a whole can also have global curvature. A book on cosmology would dedicate an early chapter to explaining curvature and giving examples of positive curvature and negative curvature. Happily, we can mostly ignore curvature in this short course. Cosmologists believe that the curvature of our universe on the largest scale is either exactly zero, kappa equals 0, an ordinary three-dimensional Euclidean geometry, or so small that it has played no role in the evolution of the expansion of our universe to date because r sub 0 is much larger than the size of our observable universe. However, if our universe is spatially finite, then it has positive curvature. And a universe with positive curvature could end in a big crunch, though our universe will not. I have simplified many results in this course by assuming zero curvature, though we will discuss it when needed. Supplemental video number 5 explains positive curvature. Zero curvature is also called a flat universe, flat space, or a flat geometry. When you hear flat in this context, do not think that our three-dimensional space is some version of a two-dimensional plane. This meaning of flat is different than a flat plane. A flat universe is ordinary three-dimensional space that you always knew before you heard the phrase flat universe or zero curvature. Parallel lines never meet. The sum of the angles of a very large triangle is 180 degrees. Ordinary Euclidean space. However, note that the curvature term is the only term on the right-hand side that could potentially be negative. So, if a universe can stop expanding, reach a maximum scale factor, and then start contracting, it can only be this curvature term that could cause that, positive curvature. Later in the course, we will come back to this curvature term when we consider different possible ends to our universe, in particular, a big crunch. We also define the Hubble parameter as A dot divided by A, which is what's inside the parentheses on the left-hand side. At some time we are interested in. At time now, the Hubble parameter is the Hubble constant, h sub 0, which is measured to be 68 kilometers per second per megaparsec in astronomer units. Previously we talked about the Hubble crisis.